Chapter 3 Matter, Energy, and the Universe. Section 3.1 The Universe and Our Solar System. So, this course focuses on the Earth, but the Earth exists in something that is much larger, a system that is much larger, something that we call the universe. We have used a variety of technologies to view what's in the universe, and we've discovered some interesting things. Of course, our solar system is part of the universe, and our solar system is defined as the sun and the 8 planets that orbit the sun. Some questions we need to ask is, how did the universe begin? Is Earth unique when compared to other planets? So, the theory that is most prevalent about how the universe began is called the Big Bang Theory. And according to the Big Bang Theory and various measurements related to this theory, the universe came into being about 13.8 billion years ago. So that's a best estimate. You'll see other numbers within that 13.8 billion year value. Don't worry about that. It's just various measurements are being used to try to determine the age of the universe. And as I said, the best estimate is probably about 13.8. Now here comes the weird part. At the instance before it came into existence, the universe, physicists believe that all the matter and energy that currently is in the universe was squeezed and concentrated into a very small area. Once again, there's various estimates about how small this area was. Some scientists say the size of a dime. Other scientists say the size of an atom. This instance before the universe existed is sometimes referred to as the singularity. When the universe was at this singularity stage, matter didn't exist, energy didn't exist, space didn't exist, and time didn't exist. Now this idea that matter, energy, space, and time did not exist at the singularity is based on some pretty good science, the best science that we have to date. So suddenly, at some moment, the universe began to exist, and this beginning, the Big Bang, caused all of this matter and energy to expand outward from the singularity at an incredible rate, and it caused the formation of matter, energy, space, and time. And as I said, this event is known as the Big Bang. Our solar system formed about 5 billion years ago. So the universe had been expanding for approximately 8.8 billion years, and at that stage, the solar system formed, our solar system. At the moment of the formation of our solar system, the universe was about 65% of its present size. So it's expanded still over this 5 billion year period. The universe continues to expand, and it's increasingly getting larger. So this graphic represents the history of the expansion of the universe, and it comes from NASA. And what's important here, they show this WMAP satellite, and this WMAP satellite has been used to confirm some of the theories about the universe. So in this graphic, NASA estimates the age of the universe to be about 13.7 billion years, so a little bit off from the number I gave. And if you take a look at this graph, you'll see it shows the timing of when galaxies and planets started developing, when dark energy started to accelerate the expansion of the universe. Back to WMAP, that afterglow light pattern at 400,000 years ago, that pattern is part of what WMAP was made to image, and what they were looking for was a homogeneous spread of matter across the universe. Notice first stars started appearing about 400 million years into the Big Bang expansion. Now, telescopes play a very important role in confirming the Big Bang theory, because telescopes are can be seen as time traveling devices. The image that a telescope produces is based on light that has traveled billions of light years. So here we see an image from the early part of the Big Bang, showing that at that time, galaxies, many galaxies, hundreds of galaxies, thousands of galaxies had formed. So, is there proof that the Big Bang occurred, or is this just a theory without proof? I'm going to list here some of the four main proofs for that theory to be correct, that there was this Big Bang. And the first piece of evidence is if the Big Bang occurred, all objects in the universe should be moving apart from each other, and astronomers confirm this, that they are moving. If the Big Bang occurred, there should be an afterglow from the explosion. So another satellite was used to measure this afterglow, and this afterglow is cosmic radiation, and we can find it throughout the universe. It exists. The extreme temperatures associated with the Big Bang should have determined what types of matter would form in the universe, and the high temperatures should have produced 25% of the matter being helium, and that's exactly what it is. And then finally, back to that WMAP satellite, if the universe occurred because of a Big Bang, matter in the universe should be distributed homogeneously, and it is. So how will the universe end? And cosmologists have postulated two endings to the universe. One, it could expand to forever, until all matter and energy is distributed across space and no longer useful. Or the universe could expand to a certain size, and then gravity would cause all the matter to be pulled back in towards the center. And this would create a big crunch. And as I said, yikes, that might hurt. Maybe the universe oscillates between big bangs and big crunches infinitely. So what do we know about the structure of our universe? Most of our knowledge is based on observations through either optical or radio telescopes. Scientists estimate the diameter of the universe is about 93 billion light years. Our Milky Way galaxy is about 100,000 light years across. So that means if you had Milky Ways, there would be almost a million of them end to end from in terms of representing the size of the universe. Gravity within the universe causes mass to concentrate randomly, forming stars, galaxies, planets. Stars are massive, large accumulations of matter, mainly hydrogen and helium gas, and they're so massive that gravity causes the material that's inside them to be pulled towards the center, and in this process, hydrogen is converted into helium. That creates a nuclear fusion reaction, produces high temperatures in the inside of a star. Those temperatures cause this are transmitted, or the heat energy is transmitted to the surface of the star, and the surface of the stars are extremely hot, in the neighborhood of 6,000 degrees Celsius. And that surface, because it's very hot, emits radiation in the wavelength band of primarily in invisible light. Stars tend to be organized in galaxies, and galaxies tend to have billions of stars within them. Scientists estimate there might be 100 to 200 billion galaxies in our universe, or maybe there could be as many as 2 trillion. So, once again, billions of stars in these galaxies. There's billions of galaxies. So how many total stars? Maybe 10 billion trillion stars. As I've mentioned, the main instruments that we use to figure things out about the universe are telescopes. And this is an optical telescope that's being built in Chile. It should be operational in about 6 years. It has a 39-meter mirror. The bigger the mirror, the more light that can be gathered, the more things that can be seen. And it's called the European Extremely Large Telescope. And it's built in Chile at a high altitude in the mountains, so that the effects of the atmosphere are minimized. To get no effect, no sort of effect on the visibility of the imaging, we can send telescopes into space. And one of the first telescopes that was sent into space to view things in the universe was the Hubble Space Telescope. And it's got a 2.4 meter mirror, and it's produced thousands of images of things that are in our universe. Not all telescopes view visible light. Some of them are designed to view other wavelength bands. So the Spitzer Space Telescope views things in the universe in the infrared radiation band. And here we see the Helix Nebula shown in infrared light. Some forms of radiation can't be seen with optical telescopes. Other types of telescopes need to be constructed. For example, radio waves. We've examined radio waves in space, and these are examined by radio telescopes. And radio telescopes receive these radio waves on a dish. There are no optics involved. So this is the Parkes Radio Telescope in Australia. There's a radio telescope pretty close to the UBC Okanagan campus. Just travel south for about an hour and a half, and in Okanagan Falls, BC, there's the Dominion Radio Astrophysical Observatory. So this is a research place, a research site. There's some UBC professors use this, astronomers, to do their research on learning more about the universe. So we live in the Milky Way galaxy. What's its structure? Now remember, the Milky Way is one of billions of galaxies, maybe 100 to 200 billion galaxies in the universe. The Milky Way is part of a galaxy cluster. It's one of the large galaxies in this cluster. There's 3 of them, and there's about 30 smaller galaxies. The diameter of the Milky Way is about 100,000 light years, and it's estimated there's anywhere between 200 to 400 billion stars in the Milky Way galaxy, and probably more than 100 billion planets. If you look at the structure of the Milky Way galaxy, there seems to be 3 different kinds of parts. There's a disk, a nuclear bulge, and a halo, and I'll define those right now. So the disk is a plane of rotation consisting of young stars, globular clusters, gas, and dust. At the Milky Way center is a concentration of young and older stars, and that's called the nuclear bulge. And then in a spherical shape, or in a sphere, is a thin cloud of stars and globular clusters that's called the halo. So that's represented here on this slide. So we can see the nuclear bulge at the center. We're about 28,000 light years from the center of the Milky Way galaxy, and there's a black hole in the center. So this slide shows us the features common to the Milky Way galaxy. So if we were to view our galaxy from above, it looks like this. It's a spiral galaxy, and this is not the Milky Way. This is another spiral galaxy. So it's spinning in space. We can't see that happening because they're so large, but the stars are moving around a center part of this feature. Galaxies come in various sizes and shapes, and here we have the Sombrero galaxy. It's in space. It used to be in the United States, but Donald Trump decided it has to leave, right? That's a joke. Anyway. Oh no, it's the unorganized galaxy. Kind of looks like my room. It's unorganized. So within the Milky Way galaxy are billions of stars, and many of those stars have a solar system. And the solar system is basically defined as a star that has objects orbiting it. And our solar system formed about 5 billion years ago. Orbiting our sun is at least 8 planets, 3 dwarf planets, about 130 satellites. So satellite is like a moon, comets, and asteroids. Most of the asteroids are found between Mars and Jupiter, in between their orbits. Most planet orbits are almost circular ellipses, except for Pluto and Mercury. Orbits of the planets are mainly tilted at about an average of about 7 degrees from the plane of the sun's equator. And here we can see the sun. This is kind of to scale. Mercury is the first planet. Venus is the second. Then comes Earth. Mars is our 4th planet. And then we get these huge gas giants, Jupiter and Saturn. There's Uranus and Neptune. And then a bunch of dwarf planets, and Pluto is considered a dwarf planet. So let's learn some more facts about the inner solar system. So we're talking about everything inside the asteroid belt that exists between Mars and Jupiter. And let's begin with the planet that's closest to the sun, and that's Mercury. And the surface of Mercury looks a lot like the moon. It's pockmarked with various craters, has a grayish tone to it. There's no life on Mercury, and the most obvious reason why there's no life on Mercury is when it's facing the sun, its temperature, the surface temperature, is about 430 degrees Celsius. When the side facing away from the sun cools to a temperature of about minus 200 degrees Celsius. So it's the first planet from the sun. Average distance about 60 million kilometers. It has a thin atmosphere, and the major constituents of that atmosphere are sodium, potassium, and helium. It has no tectonic system. The Earth seems to be the only planet in our solar system with a tectonic system. So, what is a tectonic system? It refers to the surface of a planet being composed of plates, and that these plates have the ability to move around. In the Earth's case, there are two types of plates. Plates made up of continental type rocks, and they're lighter, they float higher up in the mantle, and the mantle is that layer beneath these plates that is kind of semi-fluid. And the other types of plates are plates that are of heavier rock composition, basalts, and these are oceanic plates. They are found beneath the ocean surface. These plates get subducted underneath the continental plates as the movement occurs. And as I said, the Earth is the only planet with a tectonic system that recycles surface crust. Venus is the second planet from the sun, and here we have a radar image of Venus. Now, why did they use radar? So radar was able to penetrate the clouds that cover the surface of Venus. There are no breaks in these clouds, and these clouds are very, very thick. So radar has the ability to pass through these clouds and image the surface of this planet. Average distance from the sun is about 108 million kilometers. Mathematically, if you calculate out what its temperature should be, it should be a little bit warmer, the average global temperature, than the Earth. I think in the range of about 20 degrees Celsius. Earth is about 15 degrees Celsius. But when a satellite probe was sent to Venus, a Russian probe, it immediately burned up and melted. And it was discovered that the temperature of Venus was way higher than 20 degrees Celsius. It was in the neighborhood of 470 degrees Celsius. And this is because it has a very strong greenhouse effect. The main gases in Venus's atmosphere are carbon dioxide, carbon monoxide, and hydrogen chloride. And of these three, carbon dioxide is the gas responsible for its extreme greenhouse effect. Its clouds are made up of sulfuric acid, so not water. And its surface has many volcanic landforms, and these landforms seem to be very young, less than 800 million years old. So it has an active surface. The third planet from the sun is our home planet, Earth. And if you look at this image, there is an obvious color on our planet, and that is the color blue. And that blue color is caused by water. Land surfaces are tan color, but they do green up. We don't see this occurring on any of the other planets, any plant life. Earth is the third planet from the sun. It may have intelligent life. I guess that's all a function of whether or not we survive over the next 4 years if Trump gets reelected. Average distance is about 149.6 million kilometers, and temperatures on the Earth's surface vary from an extreme of 58 degrees Celsius found in the subtropical desert regions to as low as minus 88 degrees Celsius, and that temperature was recorded on Antarctica. The atmosphere has three main gases: nitrogen, oxygen, and water vapor. It's got a tectonic system, so the surface crust is recycled, and it's just the right size to have just the right amount of gravity to allow for the development of cellular life as we know it, and this life has the ability to build structures above the ground surface, as in trees, or even the bodies of animals. Mars is the fourth planet from the Sun, and it actually might have life. Here is an image taken in 2001, two different dates. In the June 26th image, we can see the surface clearly, the surface features. But Mars can have strong windstorms, and that's what's shown in September 4th. Now the surface is obscured, and that's because of blowing dust in the atmosphere. The other interesting feature to notice in this image is the white areas at the poles. So these white areas are frozen carbon dioxide. Average distance is 227.9 million kilometers. Surface temperature variation is from minus 133 to 27 degrees Celsius. It's smaller than Earth, has only 40% of the mass of Earth. Atmosphere is mainly composed of carbon dioxide, nitrogen, and argon. Atmospheric pressure is less than Earth because of its smaller size, about 70% of what Earth's atmospheric pressure is. There's evidence of flowing water in terms of fluvial landforms, but we don't see the water. Where did all the water go? And finally, Mars has some pretty tall landscape features in the form of mountains. So it has a mountain that has an elevation of 27 kilometers. So the highest mountain on Earth is Mount Everest, and its elevation is 8.6 kilometers above sea level. So we've just covered the inner solar systems, so now we're going to look at the planets beyond the asteroid belt, which occurs between Mars and Jupiter, and inner solar system. This is the outer solar system. And the first planet we're going to look at is the largest planet in our solar system, Jupiter. And in this image, we can see Jupiter and one of its moons, and it has many moons. Jupiter is the fifth planet from the Sun. Average distance about 778.4 million kilometers. It spins quite quickly on its polar axis, completing one rotation or one day in 9.8 hours. Its surface temperatures are warmer than would be expected from its distance from the Sun. Surface temperatures are about 15 to 20 degrees Celsius on average, and these higher surface temperatures are probably a result of heat being transported from the inner core to the surface and making that surface warmer. Inner core temperature is estimated to be about 20,000 degrees Celsius. The planet itself is composed of mainly hydrogen and helium, so gases, but because of the extreme gravity, these gases act in many ways like solids. The atmosphere is composed of hydrogen, helium, and methane. Its atmosphere moves around its surface quite quickly, so it has fast winds, very turbulent winds, and they move at a speed of about 600 kilometers per hour. The sixth planet from the Sun is another gas giant called Saturn. Average distance from the Sun, 1,424 million kilometers. It too has a fast rotation around its polar axis, completing one day in 10.2 hours. Surface temperatures are quite cold, minus 139 degrees Celsius. But it also has a warm inner core, probably because of fusion reactions taking place. The inner core has a temperature of about 12,000 degrees Celsius. Like Saturn, the planet itself is composed of mainly hydrogen and helium, and it has a similar atmosphere to Jupiter, with the atmosphere being composed of hydrogen, helium, and methane. Saturn itself has no life as we know it, but its moon Titan might have primitive life, and there will no doubt be a probe being sent to that moon shortly to take a look at that. Seventh planet from the sun is two pronunciations of this. Uranus, or if you don't have strange word fetishes, Uranus. Seventh planet from the sun, average distance is 2,872 million kilometers away, so we should expect its surface temperature to be even colder than Saturn, and surface temperatures are colder, minus 197 degrees Celsius. Its axis is nearly parallel to its orbital plane. So when we view it, it's tilted. It's tilted and spinning. We can see one of the poles spinning around. The planet itself is composed mainly of rock, so it's not a gas planet. Its atmosphere is once again similar to Jupiter and Saturn, being composed of hydrogen, helium, and methane. The final planet in our solar system is Neptune, eighth planet from the sun. Its distance from the sun, 4,499 million kilometers. Surface temperature about minus 200 degrees Celsius. It's a gas giant. Planet is composed of hydrogen and helium. And its atmosphere, like the other three already mentioned, hydrogen, helium, and methane. And it has extremely fast winds, so the winds are believed to be traveling above its surface at about 2,000 kilometers per hour. Now, poor old Pluto used to be a planet. It was reclassified and is now known as a dwarf planet. For most of its orbit, it is the furthest away from the sun, but sometimes it's closer to the sun, and Neptune is the most distant solid body. Surface temperature anywhere between minus 235 to minus 212 degrees Celsius, so let's give it an average about minus 215. Atmosphere is composed of nitrogen, carbon dioxide, and methane. It has one large moon, Charon, and has four more moons. These other four moons are quite small in size. So over the last 2 decades, astronomers have been able to peer at other solar systems nearby our own solar system, and have discovered that there are other planets. And one planet that might be quite Earth-like is called Proxima b. So this is a recent discovery. It orbits a star called Proxima Centauri, only 4.2 light years away. So we could send a probe to it and probably get information back about its characteristics. This planet could have liquid water. It's probably rocky and terrestrial, and it should have an atmosphere. So in your lifetime, you'll probably learn more about Proxima b. Now, the final slides in this presentation I put in to give you some idea of the scale of size that we're talking about when we're talking about galaxies, the universe, our solar system. How big is this? And I think a lot of students don't understand the immense distances we're talking about. So in this slide, let's begin with the Earth. There it is. There's the Earth. And we know it's large, right? It takes many hours to fly from Kelowna to Europe. It's a large body floating in space. And it exists, as I said, in our solar system around the sun, or sometimes called Sol. So there we have these distances are correct in terms of the Earth. You can see how small its orbit is around the Sun and some of the other orbits of the other planets. Our solar system exists in a grouping of stars, and that's represented in this slide. So the Sun, we can see there's its location and some of the stars close by. And those stars exist in a small little area in the Milky Way galaxy. So you can see there, in this slide, there's a point, right, in the Milky Way galaxy, and that represents that grouping of stars. The Milky Way galaxy exists in a local galactic group that I said has 3 major galaxies and a number of minor galaxies. So there's the Milky Way. The next largest galaxy in our local galactic group is Andromeda Galaxy. And this local galactic group exists in something called the Virgo supercluster. So these are clusters of galaxies. Those aren't stars, though. Those are all different galaxies with billions of stars. And this Virgo supercluster exists in a local supercluster or local superclusters. So there's the location of the Virgo supercluster and some of the other superclusters in that general area. And then finally, so to really put this to scale, to realize how large the visible universe is, so what we have here is, a supercluster is many galaxies. Those galaxies contain many stars. Here we have the local superclusters of all, of similar, containing billions of galaxies and billions of stars. And this local supercluster is found in this little part of the observable universe. So all I can say is, wow, that's big.